Okay, hello. Greetings, Dr. Nalifa. Our group will be presenting the analysis of the round robin CPU scheduling algorithm. As we know, the round robin is famous for being fair. It gives every process of small slice of CPU time so that no single task waits too long. However, this project introduced a critical twist, the context switch penalty. In many theoretical simulations, switching between processes is instant, but in our scenario, the processor has high context switching constraint, which means every single time the CPU switches tasks, it loses 1.0 milliseconds of time. This creates a difficult trade-off. If we make the time slice too small, the CPU spends all its time switching instead of working. If we make it too big, we lose the responsiveness that makes round robin useful. To solve this problem, developed a C++ simulation to test three specific quantum values, starting with small 3 millisecond to test the maximum responsiveness, on medium 10 millisecond, a middle ground approach, and large 25 millisecond to minimize the switching penalty. We also generated a first five synthetic processes with random arrival and burst time to see which quantum size is the truly optimal choice for this specific processor. Now I will pass to Gabriel to explain the methodology and implementation as in how we built the system.
Hello, I am Gabriel Gerrard Anak Tagong 102478, and I will be leading the methodology and implementation part. Our goal was to create a simulation that was statistically significant. We've implemented a custom process control block, the PCB, using a C++ struct, which was named process. The struct contain the process ID, the arrival time, the burst time, the remaining time, and the finish time. We've generated a synthetic workload of 100 processes, and each was assigned a random arrival time between 0 and 100 milliseconds, and a burst time between 5 and 50 milliseconds. And a key feature of our methodology was the reset function. This allows us to reuse the same set of 100 processes for all three of our test cases, which is the 3 milliseconds, the 10 milliseconds, and the 25 milliseconds. And this ensures that any changes in performance was strictly due to the quantum type and not a change in the workload. And we also utilize the FIFO, first in, first out ready queue, to manage the order of execution for the round robin algorithm. So moving forward to the round robin logic itself, uh, for the round robin scheduling logic, the logic followed a preemptive cycle, which the CPU fetches the next process and evaluates it against the time quantum. So in our implementation, there are two paths where if a process completes its work with a quantum, it is terminated and its finish time is recorded. And if it exceeds the quantum, it is preempted, meaning it's paused and moved to the back of the ready queue to wait for its next turn. And this ensures that no single long process can starve the rest of the system. And most importantly, we also define the context switch penalty, which is the overhead as the core methodology constraint, which we treated the 1 millisecond overhead as the mandatory cost incurred every time a processor leaves the CPU, whether it finished the work or it is interrupted by the timer. So finally, moving to the implementation part of the code. So let's look at how this was coded in C++. So this is how the process struct look, and also the reset function for the new simulation for the other test cases look like. And moving on, this is the ready queue FIFO, first in, first out, which managed the order of the execution as mentioned. And as you can see in the snippet of our core simulation loop of the round robin algorithm here. Uh, for the quantum handling, we use a mean function to determine how much time to advance the global clock. And lastly, the most critical part of our implementation is the context switch 1 millisecond overhead, which is this one, the current time plus equals the 1.0. So we integrate, as mentioned, we integrate a 1 millisecond penalty into the timeline every time a context switch occurred, meaning that our simulation doesn't just calculate the theoretical speed, it accounts for the real world non-productive time the CPU spends swapping tasks. Now, I will demonstrate the code of our simulation and also show the result of the output. So this is the code for our OS group project for the round robin scheduling algorithm. So we're gonna run this code and simulate the result for this algorithm. So this is the result for the simulation. Okay, that's all from me, and I will pass this to Dylan, who will lead the simulation results part. Thank you.
Thank you, Gabriel. Now, I will present the simulation result for the round-robin scheduling algorithm using three different time quantums: 3 millisecond, 10 millisecond, and 25 millisecond. For each quantum, we recorded four key performance metrics: total waiting time, total turnaround time, number of context switches, and total CPU overhead from context switching. The tables displayed here show the sample output from the simulation for each quantum. So let's start with quantum equal to 3 milliseconds. For this simulation, the total waiting time was 244,458.58 milliseconds. The total turnaround time was 247,167.58 milliseconds. The context switches were 957. And the CPU overhead from switching was 957.00 milliseconds. Below here, you can see the first 5 sample processes showing their arrival time, burst time, finish time, turnaround time, and waiting time. We have limited the display to 5 processes here because showing all 100 processes will make the output very long. Now, let's look at the result for the second quantum, 10 milliseconds. The total waiting time dropped significantly from 190,693.44 milliseconds. Total turnaround time also decreased to 193,402.49 milliseconds. The context switches fell to 313, and CPU overhead was reduced to 313 milliseconds. In the sample processes, you can see the improvement across the board. For example, process 4 here now finished at 457.5 milliseconds with a waiting time of 403.3 milliseconds, which is much lower than under the 3 millisecond quantum. And the last one, here are the results for the largest quantum, 25 milliseconds. The total waiting time further decreased to 168,080.22 milliseconds. The total turnaround time was 170,789.27 milliseconds. The context switches fell dramatically to 154, and the total CPU overhead was minimized to 154.00 milliseconds. Even with this larger quantum, shorter processes like process 3 and process 4 still experience notable waiting time, but overall system overhead was greatly reduced.
Now we have run the round robin simulation and we get three simulation results. There are Q1, Q2, and Q3. According to these three results, we finalized that Q1 has the largest average waiting time, average turnaround time, and total CPU overhead, while Q3 has the smallest average waiting time, average turnaround time, and total CPU overhead. In this case, this metric should ideally be lower. The lower value of average waiting time and average turnaround time mean process are complete faster and weightless for the CPU. As we can see, Q1 has the highest value as it extremely short times like force process to wait for many more cycles to complete, while the feeling of the total CPU overhead represents the time the CPU spend on doing non-productive work, which is primarily context switching. Based on the result, it shows the CPU spend the shortest time on doing non-productive work when the large quantum is used. Q1 has the highest total CPU overhead, as the very short quantum forces the scheduler to interrupt the CPU much more often. This result show that the large quantum successfully minimizes both sides of the trade-off. It provides the best throughput while simultaneously incurring the lowest performance cost.
After running the simulation and analyzing the results, we can conclude that large quantum Q3 with the value of 25 milliseconds is the most optimal for the specific processor constraint. The reason why it is the case is because Q3 has the lowest availability with the value of 1680.80 milliseconds, 8080 with the value of 1707.89 milliseconds, and total CPU overhead with a value of 154 milliseconds out of the three quantums used. It provided the best throughput as well as the lowest performance cost, successfully minimizing both sides of the trade-off.